Okay, guys. I just posted your problem set number 2. It's due in 1 week. Okay, so you had 1 week to solve it. It's due by 5 p.m. next Wednesday. You have there 6 problems. Nothing involves computer programming or things like that now. And remember, you need to submit a PDF document where I can see the scans, the photographs, or whatever you solve, or the problems, whatever method you use to solve the problems. Just upload a picture or a scan of that. Okay, so the problem set is posted, and again, it's due in 1 week by 5 p.m. next Wednesday. Okay, is that clear? Any questions about that? Okay, so let's continue. I think we had 2 problems missing from the exam, and then we'll actually solve 2 other problems. One will be regarding electrical properties, and the other one will be regarding optical properties. Okay, so we can put in practice what we've covered. Let's go. I think did we solve this one? Oh yeah, I think I told you how to solve this one. The piezoelectric one too, right? Yes, I think we did this one too, I believe. So it's only these 2 missing. So it says you've been hired at Sony. The electrical engineering team has just built an integrated circuit. Taylor, the team leader, tells you that in order for their design to work, they need you to design a metallic interconnect material that has a resistivity between 20 and 30 nano-ohms meter at temperatures between 0 and 60. The resistivity of copper at 0 degrees is 5.7, and the coefficient of resistivity is 1.13 inverse Kelvin. What would you recommend? Would you recommend copper as the material for the circuit to the electrical engineering team? Why or why not? So what equation can I use to solve this, guys?
For the one that is for resistivity,
Yeah, okay.
that
I
varies
have,
with temperature.
I have here, yeah.
That one. Rho
Yeah,
2 and
yeah, perfect. This one, right?
yes.
So I'm given the coefficient, right? I'm given the coefficient. So I'm given alpha. I'm also given the temperature of 0 and 15.7. So I'm given the resistivity, let's say resistivity 1, so rho 1, and T1, right? And then I can get resistivity 2 because I'm given also the temperature 2. So I just solve for resistivity 2. And the question wasn't really asking if I do get these values, because I remember a couple of people saying, oh, because at 0 it's already 15.7, then you shouldn't really use this material. And then that's not what the question is asking, because as long as it has this resistivity range, within this range of temperature, it's fine. So it might happen that yes, at 0 it doesn't reach 20, but maybe at 10 degrees or so, it reaches 20. And as long as it's within this range, that's fine. But then you solve it for 60, and then you realize that it actually doesn't reach to 30. at 60 degrees. So then you can say, no, I wouldn't recommend copper, right? So you solve and you get a resistivity value less than 30, I remember. I don't remember the exact value, but you will get a value that's less than 30. And therefore, you can say, no, I wouldn't recommend copper, right? Based on the above results, would you even consider doping with copper with nickel and recommend this alloy as the material of choice? What do you guys think about this part of the question?
I remember that nickel was not a good conductor.
Yeah, but
Uh,
anyways, it's not, yeah, maybe it's not a good conductor, but remember that the materials are affected, or sorry, alloys do affect the conductivity of material, and specifically of copper. If you remember the
the
slides, I
increase.
think unit, actually, yeah, the unit of electrical properties. Remember the graph for copper, right? If I dope it with other materials, and nickel was one of those options, it will reduce the conductivity, right? So if it reduces the conductivity, what's going to happen? The resistivity is going to increase, right? Because remember that conductivity and resistivity are inverse. So if the resistivity goes up, then yeah, it might actually reach this range. So yeah, probably I will consider it, right? And that would have depended, yeah, that would have depended on your answer here. Because yeah, if you got here a very large value, then you probably say no, I wouldn't consider it, right? Because if I dope it, what's gonna happen? Conductivity is gonna go down, resistivity is gonna go even, it's gonna go even higher, and therefore it's gonna go outside this range, right? So yeah, this question will really depend on what your answer to part A of the question was, right? But the right answer was yeah, probably I would, because I know I will increase the resistivity and might go or might reach to this range, at least to this part, the upper part of the range that I'm required to achieve. Okay, any questions? Okay, imagine you become an incredibly small individual, say the size of an electron. You decide to penetrate a fluorine atom and fly around on top of one of the electrons at the outer levels. In 2D, fluorine has a primitive cubic lattice. The lattice parameter of fluorine is 550 picometers. Suppose the electron travels 60 degrees parallel to the positive horizontal direction. Find the energy at which you and the electron will be pushed back. How can you guys approach this problem? There you have the equations. How can you guys approach this problem?
Can you put the problem again?
Yeah, it's
It
here.
was with the critic K.
Yes. And once you get the critical wave vector, what do you do? Because it's asking for the
I
energy.
have the relation of K with the energy.
Yes.
And
Yes, perfect. So you could have solved this two ways actually. You could have actually draw a primitive cubic lattice and find K just from let me find those slides. Let me just go to, where is it? Here. No, actually I think that was unit 1 probably. I'm trying to find, guys. Bear with me, please. Yeah. Okay. Here we go. Okay. Let me stop sharing. Let me share back. Actually, let me share my screen so I don't have to change it. Yeah. So you could have either solved by this by geometry and find critical K, or you could have just used this equation, right? That was here. It was here. You see, there's the equation, K critical, m pi over a sine theta. So you are given the angle, and you are given also the lattice parameter, so you can get the wave vector, the critical wave vector, right? Because that's the electron when you're pushed back. So, and this is the interesting part of the question, right? If you're an electron, right, flying at the outer levels, remember, and I explained that with this, right? What happens, and that's the meaning of a Brillouin zone. Remember, the electron is traveling here, and boom, it's like a barrier there. This is the end of the first Brillouin zone. So with the first Brillouin zone, so they get pushed back. Same with other electrons. Okay, they get to the second Brillouin zone. There's a barrier there. Boom, they are pushed back, and it happens on and on and on with all the Brillouin zones. So that was the idea. That was the what you guys had to understand from the question. That's why it's asking the energy in which you and the electron will be pushed back, because the electron will be pushed back once it reaches the Brillouin zone, and in this case the first Brillouin zone. So you can find the critical wave vector, and then you find the energy. How do you find the energy? It's here. Okay, it's here. Energy, you have K critical, right? That, well, in this case kx, that's the K critical. You have the reduced Planck's constant, and you have the mass of the electron, because you were given all the constants here. So you just, with that, you just find the energy with this equation here. You guys are looking at my cursor, right? You can see my cursor, right? Yes.
Yes, mister.
Okay. Okay, cool. So, and then you get the energy. Okay. And then you can explain what I just said. Explain why you and the electron were pushed back, and relate this phenomenon to the behavior of materials in real life. And then you can explain, right? Well, that's actually what happens in real life when you're pushed back, because you reach the end of the Brillouin zone. And therefore, it's like really the electron is really it's really crashing with our ear, and it's pushed back. How does that relate to the phenomenon of well, just the behavior of materials in real life? Well, that's also explained here, right? This is the idea of the Brillouin zone. Remember that we define Brillouin zones to actually define the energy levels, right? And how is it that certain electrons can occupy certain energy levels, and then they can jump from one level to the other. And so you could have just explained that, and you could have got full marks for this question. Any question regarding that? Is it clear?
No, mister. Everything's okay.
Cool. Okay, now time to solve. You already have these slides on the practical or tutorial section. So let's solve these two exercises, and I'm actually, you guys are gonna solve it. I'm just gonna guide you, but you guys are gonna solve these problems, okay? You should already have these slides. This first question, calculate the time between two collisions and the mean free path for a wire of pure copper weighing 125 grams at room temperature. Discuss whether or not this result makes sense. The Fermi energy of copper is 7 electron volts. Okay, go ahead. How can I solve this? Ideas. Let me use my, actually, let me see if I can copy this, or at least the text. Let me stop sharing this, and let me come to the whiteboard. Let me see if I can create a whiteboard. Yes. Okay. It's been created. Bear with me. Collaborate on whiteboard. Okay. Boom. Okay. Oops. What's that? Oops. Okay. Okay. Let's solve this question, guys. Ideas. How can I solve it?
Are you
No
sharing
idea.
anything?
Sorry?
Are you sharing anything?
Am I not sharing my whiteboard?
No, you're not. I don't think so. At least I don't see it.
Sorry. Give me one sec. That's weird. Wait a second, guys. Can you guys now see it? Can you see it now?
Yes, now it's sharing.
Okay, that's the question. I just copy it from I just copy and paste the question from the slides. So, ideas, how can I start solving this? First of all, what's the time between two collisions? What does that mean? And what does the mean free path mean?
It was related to the conductivity. The more time we have, the more the conductivity was.
Yeah, so yes, that's perfect. So let's start digging around that unit and let's try to find equations that I can use. Okay, if you guys find something, just start typing on the whiteboard. You can edit the whiteboard, so go ahead. I'm here just to guide you, but you need to, it's a nice step or nice common one Fernando said. Yes, the two collisions is related to conductivity. Okay, who wrote that? Unfortunately, I can't see who wrote it. Who's writing?
Me.
Okay, nice, Miguel. Okay, great. Yes,
So
you
if we
found
if
equations.
we
That's amazing. At least we found the first equations. So now I'm gonna ask you.
I have the mass, I have the conductivity in, I don't know, on internet.
Yeah,
Maybe
we
the
can Google it. That's perfect. That's great. We can Google it. Obviously, in an exam, you will be given that. You will be given a table. But yeah, you can find the conductivity on internet.
Then Fermi energy, I can use it to calculate the number of electrons. I don't know if we can do that.
How can you use it? Can you also explain the equation on your left, please?
Yeah, I can remember. I wrote it down. It was the mean free path. Yes,
Yep.
that is the mean free path.
Yep.
So C is the
It shouldn't be
yeah.
C.
This is the. It shouldn't be C.
No, it shouldn't. It should be tau. So it should be actually. Sorry
This
for
so
yeah. It should be tau.
velocity and time.
Yeah. So what is tau? Because here you also have tau in the conductivity equation. You have tau. What's tau?
Tau was the relaxation time.
Yes, that's what it's asking me, right? Tau is the relaxation time. So that you see in the conductivity equation, you have the number of free electrons times the charge of the electron squared times the relaxation time divided by the mass, right? And here you have the mean free path equals tau times what? What is that B that you wrote there?
V is the velocity, the drift
Yes.
velocity.
Perfect. It's a drift velocity. So we can make some assumptions. That's great. You actually found everything. Okay. So now let's start solving. You said you can use the Fermi energy to calculate what?
I was trying to solve for this, but I guess that we can obtain the free electrons from the Avogadro number, density.
Yeah. Okay. That's
Yes,
perfect.
that.
Yeah.
So we have
Okay.
that. We have this.
Okay. Let's
Uh,
go with. Okay. Stop, Miguel. Thank you so much, Miguel. Let's go with Fernando. Let me just erase this. Okay. That's a great explanation and a great contribution, Miguel. Thank you. Let's go with Fernando. Okay, so I like the second suggestion that Miguel did. Let's try to find the number of free electrons with the Avogadro's number. How can you do that, Fernando?
Yeah, I'm trying to figure it out.
Yeah, that's fine. Just keep thinking. Let me just write a nice tau so everyone can. Yeah, that's tau. Oh, that's actually horrible. Okay, let me use another one. Yeah, okay. And let me delete that. Okay, perfect. Okay, Jose or Becky, do you have any idea?
Mister, I can see the screen. I see the screen in black. I don't know.
That's maybe just exit and connect back again because I am sharing and everyone and like Miguel collaborated on the whiteboard, so I'm sure he can see the screen. Mari, do you have any idea what to do from here? Mari, are you there? Mari. I can't see the board. Fernando, can you, Fernando and Miguel, can you guys see the board?
Yes, Mr. I can see it. Indeed, I can start writing on there, but I don't know.
Okay, then it's probably just their internet. Okay, never mind. Okay, so let's actually do what Miguel suggested, right? But in order to do that assumption, Miguel, because you said I can find it with the Avogadro's number, you need to make an assumption then. What will that assumption be?
that our solid is monovalent.
well, it is monovalent, right? It's a pure copper. So if you actually see copper, if we see the electronic configuration of copper, so that's actually not the assumption. The electronic configuration of copper is that of argon, and I believe it's 4D, no, it's 3D10. 3D10 4S1. Okay. So that is the electronic configuration of copper. So it is monovalent. So yes, it is related to what you said, but that's not really the answer. It has one free electron, let's say. But then I need to make an assumption. I can say that the number of atoms
equals the number of electrons.
The number of free electrons is not the same as the number of electrons.
Okay.
Because I only have one electron or one free electron per atom. That's because of the electronic configuration, right? I have 4s1, so I only have one free electron in that 4s level. So I can safely assume and say, okay, I'm just going to assume that the number of atoms is equal to the number of free electrons because I have only one free electron per atom. So it's a valid assumption, isn't it? Do you guys agree?
Yes, but what
Okay.
will happen with the valence electrons? I mean the valence of the metal. It have something to do with the copper being 4s1.
Well, in this case, we're just considering, or the equation just considers the number of free electrons, right? So you just look at the electronic configuration. And if you do the electronic configuration, you can see that all the other levels are filled, except the 4s1. What's the balance of copper?
Yeah, I guess that it was +2 and +3. No, sorry,
So
+1
that's
and +2.
yeah, copper is
Plus
1
1
and
plus
2, right?
yes.
So we're just considering the 1 here, right?
Okay.
And that's because of the number of free electrons, right? You just look at the electronic configuration. That's the key part here. Look at the electronic configuration and you know that, oh, it's 4s1, so I only have one free electron, right? Okay? So then I can get the number, sorry. Okay, Fernando, now it's easy. How do you get the number of atoms? That's
Knowing that I
chemistry.
only have one electron there and the charge is 7 electron volts, I only have to use the Avogadro number.
Not really. You're given the mass. You guys remember chemistry? I think this is even from high school. Number of atoms equals 125 grams, right? Divided by, what's the atomic weight of copper? I go and look at the periodic table. Do you guys know the atomic weight of copper? I think it's 63.55. 63.55 grams. That's 1 mole, isn't it? And I know that 1 mole equals Avogadro's number atoms, 6.022 times 10 to the 23. Oops, 23. Oh, that's horrible. 23. Oh, come on. 23 atoms. Okay. So you can get the number of atoms like that. Do you guys agree?
Yeah.
And that equals NF. Okay, so this equals NF and this equals what? Calculator. Okay, let's see. 125 times 6.022 times 10 to the 23. Oops, 125 grams divided by 63.55. 022 times 10 to the 23. Okay. So I have 1.18, and please guys, if you have a calculator at hand, use it so you can correct me if I type something wrong. 1.18 times 10 to the 24 atoms, right?
Yeah,
Well,
it's
that's
correct.
in this case will be electrons, right? Because we're assuming that I have, so I can say, oops, sorry, electrons, okay? Electrons, okay, yeah, great. So that's my number of free electrons. Okay, so now I can easily solve from this equation. Let me use another color. So I'm gonna come with this. And from here, I'm just gonna solve for NF, right? NF equals what? Conductivity times the mass divided by the electron square. Oh, sorry, I don't need to solve for that. I'm sorry. I need to solve for the relaxation time. I'm sorry, guys. So relaxation time is equals conductivity times the mass divided by the number of free electrons times charge of the electron square. I'm right, right? Is it clear?
I have a question.
Yeah, go ahead.
So we need to also solve for the drift velocity. I mean v.
But we'll do that, but that's for the mean free path, because first it's asking for the relaxation time, right? I believe.
Yeah, we have the relaxation time. We have, and then we will need v.
Yeah, we'll see that. Give me 1 sec, okay? I'll go to that later. Just give me
No,
one
the
sec.
thing is that there is something missing in the exercise.
No,
The conductivity we can
nothing is
get it
missing.
from the internet, but we need the
Nothing is missing,
electric
trust me.
field. The electric field, no.
Nothing is missing, trust me.
Okay.
Bear with me. Okay. Is it okay if I leave it like that? You guys want me to solve it? Okay, we can solve it, I guess. If you go and look on the internet for the conductivity of copper at room temperature, you'll get, I have the value somewhere here, 6.96 times 10 to the 7 Siemens per meter, obviously. 5.96, yeah, times 10 to the 7. What's the mass of an electron? You guys know? You guys remember? What's the mass of the electron? Mass of the electron is 9.11 times 10 to the negative 31. Okay. 9.11 times 10 to the negative 31 kilograms. And F, I have it here, 1.18 times 10 to the 24. Times the charge of the electron. What's the charge of the electron?
1.609 to times 10 to the minus 9, I guess. Yes.
19, I believe, right?
19.
Joules. Yeah, I believe it's 10 to the negative 19 joules, I believe. Yeah, 1.602 times 10 to the negative 19. Yeah, it's 19 joules, I believe. Okay, so let's plug that in the calculator. Times 10 to the 7 times 9.11 times 10 to the negative 31. Oops. Okay, that divided by 1.18 times 10 to the 24 times 1.602 times 10 to the negative 19. What did you guys get? Mm, 24 divided by 5. Yeah, I think it should be right. What do you guys get? Okay, tau equals, what's the value of tau, guys?
I'm sorry.
Okay. Should be electrons, so let me write it nicely. Electrons, okay. This should be negative 19. Let me write. Oops, sorry, what did I do?
2. Where is it? 2.87 times 10 to the minus 28.
Yeah, I got the same. Okay. Yeah, okay. Let me just write that down because I got the same. Oops. 2.87 times 10 to the negative 28 seconds, right? Okay. Does it make sense, guys? Do you guys think this result makes sense? Because that's also asking, right? Actually, I think it should be seconds per centimeter cube, if I'm not mistaken. Just work out your units. Kilogram joules. Yeah, it might be per centimeter cube. Because we didn't have the density, right? But yeah, so does this result make sense, guys? What do you guys think?
I think this is just too fast.
Yeah. So, and that is usually the relaxation times for good conductors will be around 10 to the negative 15, 10 to the negative 16, even 10 to the negative 14, okay? 10 to the negative 28 is very fast. So that will be an option, right? I would definitely say this is probably too fast. The time between two collisions, again, for good conductors, usually it's around 10 to the negative 15, so order of magnitude, right? 10 to the negative 15, 10 to the negative 16. Getting 10 to the negative 28 is very, very quick, okay? But okay, just because I came up with data, right? It's not that I found this problem. I just came up with the numbers. That's why we probably got this number. Okay, now let's solve for the second thing, the mean free path, right? Mean free path equals velocity times tau. So you said we need the drift velocity, Miguel, right? Because I have tau already. I found it. Okay, this is the value of tau. Great. Now I need a drift velocity. I actually can assume something. I could easily say that the drift velocity, let me use another color, I could safely assume that the drift velocity equals the Fermi velocity. I could assume that for this problem. And because I'm given the Fermi energy, that's why you work out with things that you're given, right? You're given the Fermi energy. This is actually a valid assumption, right? Because the drift velocity, if we're talking about a good conductor, actually, yeah, the drift velocity is the velocity of those electrons jumping at the other level. So I can safely say, yeah, the drift velocity is actually the Fermi velocity. Now, I'm given the Fermi energy, right? I'm not given the Fermi velocity. How can I find the Fermi the Fermi energy from the Fermi velocity, guys. Sorry, how can I find the Fermi velocity from the Fermi energy?
I have an equation. I guess I was writing it previously that
Okay,
says
go.
that
What does it say?
velocity equals the drift velocity times 1 minus exponent. I have an E. I don't know. I can remember if it was the electric field or the energy. So
Okay.
here, mm, times a time. No.
Okay.
Another equation could be the one that is related to the quantum theory.
Okay.
That relates the conductivity with the Fermi velocity.
Yeah, but how can you get, because you're given the Fermi energy, right? That's the key. You're given the Fermi energy. And I need to get to the Fermi velocity. Yeah, I mean, we could use this equation probably. There's another simple, more simple way to solve it. Let me work your equation out. Yeah, okay. Give me 1 second. I need to look something. Okay. We could actually use these equations. We know that we know that the energy, let me use now, actually let me use black. We know that the energy equals the momentum squared divided by 2 times the mass of the electron, right? We know that equation. So from this equation, I can solve for momentum. So momentum equals, what will be square root of 2 E, right? E being the energy, right? E being the energy. So that is all right. Now I also know that the momentum equals the mass times the velocity. Right? Oh, sorry, velocity, so it doesn't get confused. Mass times velocity. So I can say that the mass times the velocity equals 2me, right? And I can solve here for the energy because I have the mass and I have the velocity. I can, obviously I'm assuming that the velocity is the Fermi velocity. So I can say energy equals, oh, sorry. I need to get, no, I have the energy. I need to get the velocity. I'm sorry. So I can assume again that velocity, drift velocity is the Fermi velocity. And so the Fermi velocity equals the square root of 2 times the mass times the energy square root of that divided by the mass. You guys agree with that? Okay. And I am done. I can just solve for the Fermi velocity. I can replace. So now this equation will look with something like this. Mean free path equals Fermi velocity times tau. I have tau, I get from the Fermi velocity from here, and done, I get the mean free path. Is it clear, guys?
I didn't know that we can use that equation. Maybe
Yeah.
the exam will be in like 5 minutes trying to solve the other one.
Okay.
5 points less in the.
Yeah, I mean, you can use it
Great.
because you're assuming that the drip velocity equals the Fermi velocity, right?
Yes.
And that is a valid assumption because we're talking about a conductor.
But what about the temperature? I mean,
It was
it
just
would be
useful.
different, the energy.
What do you mean about the temperature? We're
Okay.
talking about room temperature, right?
Mm-hmm.
The problem is being clear about room temperatures. That's why I got the conductivity at room temperature.
And that is the energy at that temperature.
Yeah, obviously.
Okay.
Yeah, obviously.
Okay.
Yeah.
It's okay.
That's the Fermi energy dependent temperature, guys. That's actually a good question for all of you. That's the Fermi energy dependent temperature.
No, I was confused with the distribution.
Yeah, okay. Okay. Remember the Fermi energy doesn't change with temperature, right? Okay. That should be, then you just plug the numbers and then you get, I think that should be clear. Actually, what do you guys prefer? Because I don't think we have enough time to do the second problem, or actually, we might have at least two. Yeah, let's actually do the second problem. Then you just plug the numbers and then you'll get the answer. That's easy. Let's do the second problem. Let me copy and paste it. At least we can start the problem. Oops, yeah. Go text, and there we go. Oops, that looks very small. Okay. Okay. Now, oh, why did it copy like that? That's horrible. Okay, this should be 10 to the 12. Let me use 10 to the, oops, nope, I cannot. Well, it should be 9 times 10 to the 12, okay? So, actually, can I use, for some reason, I cannot edit this. Well, you guys have the problem, right? So I'm fine with that. You guys have the problem. So just make sure it's not 9 times 1012, right? It's 9 times 10 to the 12 inverse second. Is the reflectivity increasing or decreasing with temperature explained? Okay, first step, guys. What can I do? This is optical properties, right? That's talking about reflectivity.
We need to define the model.
Yes,
I mean the
perfect.
frequency.
What model do you think it fits on? Because the frequency is times 10 to the 12, and I know that the Hagen and Rubens relationship works actually pretty well up to at least 10 to the 13. That means the infrared region, that's up to usually 10 to the 13 inverse seconds. So I can safely say, yeah, I'm actually in the range of low frequency infrared region. So I can work with the Hagen and Rubens relation, right? Now it's talking about gold. Can I use the n minus 1 divided by n minus 1 or something square equation? I cannot use that equation. Just look at your slides because that's for insulators, right? And gold is not an insulator, you guys know that. So the equation I need to use is reflectivity equals 1 minus 4 frequency divided by conductivity. Well, that's AC conductivity, but remember that we can assume, we can make two assumptions here. Well, actually, just one. We can assume that AC conductivity equals DC conductivity. Oops, sorry. So we can just go and Google, right? The conductivity for gold. Just Google it. And also, what else do we need to Google, guys? What else do we need to Google?
The vacuum permittivity.
Well, it's not vacuum permittivity. How is this called? That's called the dielectric constant for gold. Okay. So that also Google that. Okay. You can Google that, and actually then you have everything else because you have the frequency, you have the conductivity, you have pi. Oops, that actually looks horrible. Pi should be up here. Pi, and you have the electric, and that's just 1 minus 4. Just plug the numbers, and then you get a value. So do it by yourself, and then next week we can check the answer. And also focus on this part. Is the reflectivity increasing or decreasing at this frequency when the temperature is increased? Think about that too. About that. And come back with the answer next week, okay? Questions. I think the equation is simple and you guys have all the values, right? Or am I mistaken? You just need to go and plug the values because you have everything else there. And just find the reflectivity. Remember that reflectivity is, well, in this case, you'll get a number from 0 to 1, right? And represent that as percent. Is it clear, guys? Are there any questions?
No, it looks like it's okay.
Okay. Well, then that'll be it for today's class. Try the problems by yourself, try them on your own, and come back and ask questions, and if you have any, obviously, right? But yeah, that'll be it, guys. Thank you so much, and see you on Monday, I guess. And I don't know where everyone else is, but